He knows a lot about the science stuff, Professor Dave explains.
In the previous tutorial, we introduced the concept of a harmonic oscillator and investigated such a system in a classical context. Now it's time to extend this concept to the quantum world and examine the quantum harmonic oscillator. Now, as we know, the quantum world is that which deals with tiny atoms and subatomic particles, so we are no longer looking at a macroscopic ball on a spring when discussing oscillations. We are now describing oscillations or vibrations around a point of stable equilibrium in the context of binding energies and electron orbitals. So these are oscillations of a fundamentally different nature, but they can be described using the same type of mathematics all the same. In the classical situation, we started off by talking about Hooke's law as an extension of the harmonic motion we learned about in the classical physics series. This is typical of any mass spring system. The quantum analog of this scenario could be that of an electron close to an attractive potential, or an atom subjected to a molecular potential that may look just like a harmonic oscillator within a certain limit. Take the case of an electron near a positively charged area. This electron will tend to move towards the minimum potential point, which is close to the positive charges. As it travels away, assuming it has a low enough energy, the attraction to the positive center will pull it back. Now take the example of an atom in a diatomic molecule. We know from our study of organic chemistry that covalent bonds can stretch, and the potential energy of the system varies depending on the internuclear distance. Here, the interatomic potential energy is described by the Morse potential, which is really describing the vibrational dynamics of the system. We actually learned about the Morse potential all the way back in general chemistry when learning about covalent bonds. Here, we will only investigate the harmonic oscillator rather than getting into the details of real systems, as models that describe nature on the molecular level generally have very complex potentials that are difficult to deal with mathematically. But in some cases, and for low enough energies, it is possible to approximate the potential with a simpler model, such as the harmonic oscillator. And in looking at this image, we should be convinced that, at least for low energies, the harmonic potential is a good approximation to the Morse potential. So if we solve for the eigenenergies of the quantum harmonic oscillator, it will give us insight as to how more complex systems behave. With this context understood, it's time to do some math. We will follow the same procedure that we did when talking about the particle in a box. First, we will find the Hamiltonian, and then we will solve the time-independent Schrödinger equation. Fortunately, given what we learned when going over the classical harmonic oscillator, we already know what our potential looks like, and this will be a great starting point. So here is our potential, V of x equals 1/2 kx squared, which is what we would use for a macroscopic ball on a spring. To translate this to the quantum world, all we need to do is swap the variable x for the position operator x hat. Now we can solve the time-independent Schrödinger equation. First, let's recall the equation in its general form. And now we can simply plug in our potential in place of V of x. Now, in the previous tutorial, we compared the differential equations for the classical and quantum scenarios, but we didn't specify the quantum mechanical equation to that of the harmonic oscillator. We can actually do that quite easily now if we compare them. Remembering the form of the equation for the classical scenario, we can put the other version in the same form if we just subtract E times psi from both sides, and then factor psi out from these last two terms. Now we can quite clearly see that where we have the second derivative of psi of x with respect to x in one equation, we have the second derivative of x with respect to time in the other. And where we have this parenthetical times psi of x in one, we have beta squared times x in the other. So what can we say about these two equations? We must understand that they represent completely different problems. The quantum equation tells us the allowed states for the x-dependent wave function psi of x. Notice that this second derivative with respect to x and this position operator squared are both operating on the x-dependence of psi of x. There is no explicit time dependence in this equation. We are solving a static problem. This is why we are able to use the time-independent Schrödinger equation. By contrast, the equation used for the classical scenario does have an explicit time dependence that is clearly visible in the first term, the second derivative with respect to time. In the classical scenario, the concept of a particle's wave function simply does not exist, and it would be absurd to calculate the allowed eigenstates of a classical particle in a harmonic potential, because all eigenstates are allowed. Also, we now face a much more difficult differential equation. Until now, we have been solving versions of the Schrödinger equation with no x hat squared terms, and we found solutions for psi of x that were either complex or real exponentials. That will no longer be the case, so let's slowly work through the math until we get some results we can understand. First, let's rewrite the equation for the quantum harmonic oscillator, starting out with multiplying everything by -1. So we lose the negative sign out front, and we can just rearrange the terms in the parenthetical, thereby inverting the sign of each. Next, let's multiply through by 2m over h bar squared. That cancels out these terms out front and places new ones before the second term. Let's also define a new constant, gamma, as being equal to this term here, and then distribute it through the parenthetical. That leaves us with this. Now, what we really want to do is get rid of the constants and get the equation in this kind of form, as this is something that we would be able to solve. Notice that we changed lowercase x into capital X, and we changed gamma e into epsilon, where big X equals little x over alpha, and both epsilon and alpha are new constants that have yet to be determined, which will allow us to express the equation in this manner such that it can be solved. Now we need to find what these constants must be in order to make this possible. Of course, this entails finding an equation for psi of big X instead of little x, so we also need a partial derivative operator with respect to big X instead of little x, so we are going to need to use the chain rule. Taking this partial derivative with respect to little x as operating on psi of big X, we would end up with d big X over d little x, but then we would need the derivative of what's inside, so that's d over d big X. Now, based on the relationship we just defined between little x and big X, we can replace this big X with little x over alpha. The derivative of this expression with respect to little x is simply 1 over alpha. That means altogether we have 1 over alpha times d over d big X. Now, in the equation we are trying to get, we need the second partial derivative with respect to big X, so let's square what we have here. That gives us 1 over alpha squared times d squared over d big X squared. Let's now plug this new expression in where the old second partial derivative used to be. We can then multiply through by alpha squared, which leaves us with this. Now remember that we want this equation to resemble the equation we highlighted before. This means we will need to get rid of these items in the third term. We can do that by setting their product equal to 1, so let's go ahead and say that gamma k over 2 alpha to the fourth equals 1. And from this, we can find the expression for the alpha constant. We simply multiply both sides by 2 over k gamma, and then raise to the 1/4 power. Let's follow the same logic for the second term. We need gamma e alpha squared to be equal to epsilon, and here no work is necessary. We have an expression for epsilon. And with that, we have simplified the Schrödinger equation to this more manageable form. Now let's go ahead and write this slightly differently. Let's factor psi of big X out of the second and third terms, which gives us this parenthetical, epsilon minus big X squared times psi of big X. Now to solve this, we can look at some limiting cases to infer partial solutions, and from there we can generalize to get full solutions of the equation. First, let's think of one extreme case where big X is much larger than epsilon. Under this assumption, epsilon becomes negligible, and the equation will reduce to this, the second partial derivative minus this other term. Now, the solutions for this equation happen to be of this form. We must understand that the positive exponential can't be part of the solution, since the wave function would not be normalizable. This is because exponentials with positive exponents grow indefinitely, which would make it impossible for the wave function to integrate to 1, which is the normalization condition. So if we eliminate the second term, we are left with this. But once again, this solution only works when big X is much larger than epsilon. What else is possible? Well, let's try a trick. Let's assume that the solution is not the one we just found, with a as a constant, but a more complicated function, where a is not a constant, but an x-dependent function, g of x. So we are assuming a solution of the following form. The reason we are doing this is that when we initially solve the differential equation, we are finding the shape of the solution at a certain limit. We want to delimit the possible types of solutions, and looking at x as it goes to infinity is the easiest first step, because here there can only be two possibilities. 1, the wave function grows indefinitely, or 2, the wave function goes to 0. If it doesn't make sense for it to grow indefinitely, the solution must contain a negative exponential term. Looking at this Gaussian curve, a reasonable representation of a wave function, it's as though we are initially solving for psi of x in a region where it does not depend very much on x. But in the center of the Gaussian, it does depend heavily on x, meaning that psi changes a lot in this region as x changes. So we initially assumed we were solving in this limit of very large x, and thus found the exponential tail. But now we want the full solution, which entails x dependence. Now let's see how this solution works. To do this, we can plug it into the Schrödinger equation for the harmonic oscillator. So in place of psi of x, which appears twice, we will place our solution. Let's now solve this, which will require evaluating this second derivative from the first term. Let's do this one derivative at a time. The first derivative will require the product rule since we have a product. So we get the derivative of the first function times the second function, and we add to that the first function times the derivative of the second function, which here involves bringing negative 2x over 2 out front, or simply negative x. So we end up with a difference instead of a sum, and one extra x term. Now we must get the second derivative, so we have to differentiate again. Since we have a difference, we can split this up and differentiate each term separately, each of which will require the product rule. For this first term, we get the derivative of the first function times the second function, and we add to that the first function times the derivative of the second function. So that gives us the second derivative of g of big X with respect to big X, and then again we just get the difference instead of the sum and an extra big X term. Moving on to the second term, this is a little trickier as we have the product of three terms. Let's pull this negative sign out and place the rest in a parenthetical, so we get the derivative of the first term times the second and third terms, then we get the first times the derivative of the second, just this big X times the third, and then we get the first and second times the derivative of the third. Simplifying now and distributing the negative sign, the first term works as it is. We can just bring the big X up front. For the second term, the derivative of big X with respect to big X is simply 1, so that goes away and we get this. And then here, one more time, we get a negative big X out front when we differentiate this, so we can combine that with the other big X to get negative big X squared times the other two functions. And then when the minus sign distributes here, it becomes positive. Lastly, we do have one term that appears twice, so we can simply combine them, which means we just double it, or make this 2 big X instead of 1. Now let's plug this lengthy expression back into the Schrödinger equation. Dividing through by e to the negative x squared over 2 will simplify things a bit. Then, if we expand this parenthetical, we notice that these two terms add up to 0, so we can remove those. Then we factor g of x out of these two terms, and this is as simple as we can get it. Now, it turns out that this is the canonical linear homogeneous second-order ordinary differential equation, w double prime minus 2z w prime plus lambda w equals 0, where w represents g of x, z represents x, and lambda represents epsilon minus 1. This equation is known as the Hermite equation. Its solutions are the Hermite polynomials, which take on this general form. We will leave a detailed discussion of the solution of this differential equation for the mathematics series, and simply take it for granted here. Now we can easily find some of the Hermite polynomials by plugging in values for n. For example, when n equals 0, we plug in 0 for these two locations. This first exponent makes this parenthetical equal to 1, and then taking the 0th derivative basically just means that we are not taking the derivative at all, so the expression is unchanged. These terms have the same exponent but opposite in sign, so when multiplying through, the exponents add up to 0, and e to the 0 is 1, and 1 times 1 is 1, so we end up seeing that h sub 0 equals 1. When n equals 1, we plug in 1 everywhere, which makes this a first derivative, and we get this expression. With the negative exponent, that's the same as making the exponent positive and putting the term in the denominator, which actually allows us to cancel these two terms, so we end up seeing that h sub 1 equals 2x. When n equals 2, that means we need to take a second derivative, so we can just differentiate the first derivative, which requires that we use the product rule. And that leaves us with h sub 2 equals negative 2 plus 4x squared. So we can see that Hermite polynomials are regular polynomials that grow in order as n increases. In any case, remember that our solution for the wave function also contains a real negative exponential, so it can now be represented like this, with h sub n of big X in place of g of big X, followed by e to the negative big X squared over 2, like before, and that's where we end up. This is the mathematical representation of the eigenstates of a quantum particle in a harmonic potential. Okay, so now as usual, we need to make sure the wave function is normalized. Let's start with the easiest one, h0. The normalization condition, as we recall, involves setting the integral of psi star times psi equal to 1. So let's plug in our expression for psi, and then plug in 1 in place of h0. Since there are no complex terms here, psi and psi star are identical, so we can simply square the expression, which means that these exponents will add together, and a negative half of negative big X squared minus another half of negative big X squared equals 1 full negative big X squared. Now the integral of this expression happens to be equal to root pi. It is possible to find a general normalization condition for all the n orders of the solution. However, this solution involves complicated factorials and is too long to derive here, and since this is a known solution, let's just take this for granted as the general solution for the harmonic potential. Once we know the normalization factors, we can easily find a solution for psi 0 of x, and then this expression for the general form of the normalization factor for the wave function in the harmonic potential, with the Hermite polynomial. All we need to do is multiply the unnormalized wave function by 1 over the square root of the normalization factor. The square root of root pi is pi to the 1/4. So the wave function for the 0th order is simply 1 over pi to the 1/4 times e to the negative big X squared over 2. We can perform the same operation with the generalized normalization factor to obtain the full solution for all orders n of the wave function. Before analyzing the wave functions, let's go ahead and calculate the eigenenergies. Let's start with the eigenenergy for n equals 0. So let's set h naught of big X equal to 1. Plugging that into psi naught of big X, we get 1 times e to the negative big X squared over 2. Then we can plug this expression for psi naught of big X into the Schrödinger equation, so that now looks like this. The first thing we have to do is take the second derivative of this expression. As we know, a second derivative is just the derivative of the derivative, so let's get the first derivative first. Using the chain rule, we get negative 2 big X over 2 times the original function. The 2's cancel out, and we have negative big X times the original function. Now we have to take the derivative again, and this time we need the product rule. So that's the derivative of the first function times the second function plus the first function times the derivative of the second function. The two derivatives are easy. The first is just negative 1, and the second is the same as the result from the first differentiation. So that gives us this expression. Now, plugging this second derivative back into the whole equation, we end up with this expression. We can divide both sides by this exponential term, so that will just go away, and we are left with negative 1 plus big X squared plus epsilon naught minus big X squared. Canceling the big X terms and rearranging, we are left with epsilon equals 1. Recall that we had epsilon as being equal to gamma E alpha squared, where alpha equals 2 over k gamma to the 1/4, and gamma equals 2m over h bar squared. So let's plug in these expressions in place of gamma, E, and alpha right here. Notice that the 1/4 power becomes 1/2 as this term is squared. We can plug in for this gamma in the denominator as well, which means we get h bar squared over 2m, so the 2's cancel and h bar squared can be pulled out by taking the square root to put h bar right here. That cancels out an h bar on top and bottom. Then another thing we can do is take the m here and make it m squared inside the parenthetical. That cancels out an m on top and bottom inside here. And remember, all of this equals 1. And from this, we can solve for the energy, E naught, which will equal h bar over 2 times root k over m. If we define omega as root k over m, this becomes 1/2 h bar omega. This right here is probably one of the most important and famous results in quantum mechanics. What this tells us is that the ground state of the quantum harmonic oscillator has a non-zero energy. Given how much work it would be, we will not derive any of the other solutions, but it is possible to work out the eigenenergies for all eigenstates, which are given by this equation, E sub n equals the quantity n plus 1/2 times h bar omega. Let us now compare this to the result we found for the classical harmonic oscillator, E equals 1/2 mv naught squared. For this, when the initial velocity of the particle is 0, energy equals 0, a rather intuitive result. But in the quantum case, the lowest allowed energy is 1/2 h bar omega, which is inversely proportional to mass, given what omega represents. Now, although this is a non-zero value, it is incredibly tiny because h bar is very tiny, equal to 1.054 times 10 to the negative 34 meters squared kilograms per second. However, when a particle's mass is extremely tiny, such as when dealing with a subatomic particle, this value does become relevant. Now, with the solution for the Schrödinger equation complete and the eigenenergies derived, let's move forward and complete our investigation of the quantum harmonic oscillator by interpreting and applying our results.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.